All right, continuing on with class 11, I believe this is video 4 for the class. Noteworthy that we used this equation now that I'm having as our go-to equation for incorporating Bernoulli with external stuff, right? So we're going to have this guy right here is going to be what we call the shaft head, and that could either be a pump, which is going to add head to the system, or it's going to be a turbine, which extracts head, and we could also have some head losses, right? And if you want to have something similar, the equation out of your textbook, this looks very much a lot in common right there. You'll notice that they include both the pump and the turbine. They have the state 1 on the left, they have state 2 on the right, whereas I have them the other way around. And they also have the losses on the right-hand side right there. This is a good figure. I like these figures right here. I'm trying to remember what, I think it's called a Sankey diagram. That's my recollection. Sankey diagram, I think it is. Where you can kind of see sort of an energy accounting about where some of the stuff goes. And when it comes to efficiency, you can see that we're gonna take a hit in each of the transfers. For the thing, like we could take a hit when we put pump power in. There's some that get lost. When we try to extract some because of the turbine, we lose some. Like we can't get out as much as we put in. And even with the whole the operation of the system, we have head losses. So there's going to be some loss of efficiency right in there. So what you want over what you paid for is the rule when it comes to efficiencies. And the same thing true with motors and generators. And I had all these nice things and I didn't use them. I should have used these. So we did this example in the previous video. We're going to do this example now. So we have a hydraulic turbine is at the bottom of this, I don't know, it's some body of water and some caverns, and we're going to try to extract energy out of this. And it's allowed, we're able to flow out 8 million gallons per minute. And the depth of this turbine from the free surface, which we assume to be constant, of course, with climate change and whatnot, we're losing the Colorado River. But this is sort of like the idea. This is, I guess, maybe this is like the Hoover Dam, or someone in class pointed out that this was some amount of the parameters that were at least at one point true for the Hoover Dam. So, what is the maximum amount of power output possible? Why will the actual amount be less? Is what we're asked. So here we go. So first off, let's turn, I guess, the volumetric flow rate. We know that it's 8 million gallons per minute. Let's turn it into cubic feet per second by dividing out by 7.48 gallons per cubic foot and 60 seconds per min. So we get the more useful to us cubic feet per second. So we get 17,830. So we're going to need this here in a second. We want to try to find out from this spot, like up here maybe, to this spot just outside, or I guess it needs to be in a streamline, doesn't it? So there's a streamline, because Bernoulli's always about a streamline. So let's say it's to the center of this thing right here. But we'll see in a second, we're going to do a what if kind of thing. So we're going from 1 to 2. So I've been writing my Bernoulli 2 like this way. And we're going to add, nope, excuse me. Remember, this is a turbine, so we have a minus head of the turbine and then minus head losses. All right. So we write this out and then we start thinking about what we're doing here. So first off, we have the maximum power. The maximum amount power. So I have to kind of think, well, what's the scenario under which we have the maximum power? First off, this is going to be atmospheric pressure. That's time. We're going to the discharge of the outlet right in there. And we're coming from the top of this lake. So both of these are atmospheric pressures. We'll also say that this down here, this is the datum. So I can go ahead and say Z2 is equal to 0, right? Because that's where the height of 2 is going to be. And let me say that we're going to have this right here, because we're going to say that it's the maximum possible. So we're going to say, well, there's no losses that are taking place, and maybe the friction that's taking place here, or even some of the friction at the outlet of the turbine. And here's one where we have to do a little bit of an imagination. We're going to say, what if this was huge? So if we had a huge outlet, V2 would be very, very small. I guess I'll just write small, very small, right? As the area of the outlet gets very small, so we could say that this is very small. Because we want the maximum possible, so we want this to be as small as we possibly can. So let's say this is so small that it's not going to matter. And then up here, this is stationary. So what we're really left with, if you look at this, is that Z1, or I should say the turbine head, is going to be equal to this elevation, which is equal to 600 feet. So max possible, it's going to be because of this. Now, that's not really practical. I mean, they're going to have losses. It's not going to be a trickle coming out of here. So it's got to have some amount. I mean, you can just imagine it's going to be thunderously loud. But this is what the head is. And it gives you reinforces that idea of why we're using head, because this dimension is the thing that's really driving our ability to extract power. And so the turbine extracted power, as you'll recall, is going to be HT times gamma times the volumetric flow rate, or 600 times 62.4 times the 17,830, and divide by 550, because this right here will turn into foot-pounds per second. This will convert it into horsepower, and so what we find is we have 1,210,000 horsepower. That's a lot of horsepower, but why will the actual amount be less? Because losses due to you can say turbulence. We don't know yet. We haven't covered yet that there's this thing called, we have friction that is taking place right here. They actually think of it as fluid friction taking place. So the viscous losses really that are taking place in there, and there's going to be turbulence as it gets back into this thing, and those increase with that due to losses due to viscous. I'm sorry, I misspelled viscous. It doesn't matter, right? Viscous. I still going to spell viscosity. Viscosity. There you go. But of course, Bernoulli ignores viscosity, but they kind of show up in that term later on for us. Turbine inefficiency. So we call it efficiency, but it's really inefficiency. We could have outlet velocity, because we ignored the outlet velocity here. We said it was the outlet diameter was so huge that it had a very small outlet velocity, but we know there's going to be some, right? That they could so we can have so those are the reasons why the actual amount are going to be less. We also need to put it through a generator, so we're going to have a generator inefficiency. So we're going to take a hit in a bunch of different ways. We're not going to get this amount out, but this is the maximum possible that we could. So that's example 2. We'll do a third example in video 5.